In Chapter 5 in Class Problem 2, we're going to go over how to analyze a Rankine cycle. In this problem, we're dealing with a power plant that uses a steam-driven turbine generator that's incorporated into a Rankine cycle. And the turbine operates optimally, so that's an important keyword, where the input steam is going to be 525 degrees Celsius and 9 megapascal pressure. The outlet from the turbine, or the exhaust, is operating at a pressure of 20 kilopascals. What we want to do is we want to find the operating conditions for all the pieces of equipment in the cycle. So that includes the boiler, turbine, condenser, and pump. We also want to estimate the overall efficiency of the cycle. And then if the cycle is supposed to produce 10 megawatts of power, then what we want to estimate is what is the mass flow rate of steam needed in order for that cycle to produce that amount of power. Based on this problem statement, we could sketch a schematic that looks like this, right? Where we have our Rankine cycle where the steam first passes through the boiler where it receives some heat, and then it passes through the turbine where some work is extracted from the steam. The outlet from the turbine then goes into a condenser where it's condensed back into a liquid, which is then passed through a pump, which gets it back up to a high pressure. And so, with the different steps of the Rankine cycle, typically some assumptions that are made about the different pieces. For the boiler and the condenser, these are typically assumed to operate isobarically, where the pressure going in is the same as the pressure going out. So that would be true for both the boiler and condenser. And then for the turbine and the pump, these are typically assumed to be operating under adiabatic conditions, okay, so that there's no heat leaving either the turbine or the pump, okay. And so I also sort of sketched out, the pieces of information that we know. So we know some of the temperatures, some of the pressures. You could see here for the condenser, right, the pressure P3 is going to be equal to the pressure P4 there, okay. So I listed the information we have here. And to do this analysis of the Rankine cycle to figure out all of the operating parameters, just like with our previous mass, energy, and entropy balances, we need to make some assumptions. As far as the assumptions we need to make, for each piece of equipment, we're going to treat them as an open system. Treat each unit, operation, as open system, okay? Because mass is crossing the system boundaries, right? Steam is going in and out. Similarly, these parameters aren't changing with time, so we're going to assume that the cycle is also operating at steady state. We're not going to worry about changes in kinetic or potential energy. And in this problem, because we're dealing with steam, we're going to use the steam tables. All right. As far as other sorts of assumptions, I'll kind of list them out here. So once again, with the turbine and the pump, we assume that they are adiabatic. No heat leaves them. So Q dot is equal to 0. And for the boiler and condenser, those are going to be isobaric. Okay. So here, constant P. Also with the boiler and condenser, right, there's heat going in, but there's no work involved with a boiler and condenser, right? There's no shaft work. So we'll also write also no shaft work. Inherently, there's nothing really like spinning or anything in the boiler or condenser. It's just providing heat or removing heat. Okay. One other assumption we have to make has to deal with that comment about how the turbine operates optimally. Okay. And so what this suggests, if it's operating optimally, that there's no energy or work that's lost uh, in order to change the entropy, right? In order to generate entropy. So that's basically what this optimally means. So turbine operates optimally, so it's operating reversibly, right? So that there's essentially no inefficiencies with the turbine. And what that means is that for the turbine, the S-gen term is going to be just equal to 0. Okay, so that's going to help us with our analysis. The last sort of assumption that's typically made when you're dealing with a condenser is that the outlet stream of the condenser is just going to be a saturated liquid. Okay, so that since we know the pressure, we're also going to assume that this stream is saturated. So that gives us two pieces of intensive information, and that will allow us to look up any other property in the steam table. Okay, so those are the assumptions we're going to make in this problem. And because we're dealing with such many different components in our cycle with a lot of information, it's important to be organized. And so what we could do is we could kind of set up tables that look like this, which contain all of our information. So this first table is going to contain our pressures, temperatures, and also our enthalpies and entropies. So this is where we will record everything. And then this table basically allows us to track the changes in the enthalpy uh, between each unit operation. And then that will allow us to relate it to whether it deals with the shaft work or it deals with heat in that unit operation.